Today we're going to start off our new unit on polynomial expressions and equations. So flip over to page 1 and we'll get started. The first thing that we're going to do is we're going to look at a couple definitions. And we're going to start by simplifying 3x times x minus 2 plus x plus 6 times x minus 2. So if I am to rewrite that, all that means is I am going to distribute the 3x I am going to FOIL the x plus 6 and the x minus 2. And then I'm going to collect like terms. Those cancel. Minus 12. So we have the expression 4x squared minus 2x minus 12. Well, and then we get to the first question. Is the resulting expression a polynomial? Well, to answer what a polynomial is, we're actually going to flip over to page 5. So flip over to page 5 and we'll take a look at what a polynomial is and how to figure out if an expression or equation is a polynomial. Now, the technical definition of a polynomial looks like this, which is long, confusing, and hard to understand. So I want to simplify it to two simple ideas. Idea number 1, it is an equation or expression with whole number exponents on x. So the first requirement is whole number exponents on x. The second requirement is real coefficient. The coefficient, or the number in front of the x, has to be a real number. Now, basically all that means is, well, we can't have an x in a denominator. We can't have x as part of a square root or x as part of a log. And we can't have x as a fraction. We can't have x to a negative exponent. Everything else is pretty much fair game. So if we look through all of these examples that are polynomial functions, you'll notice that every single exponent on every single x is a whole number. Now you could say, well, Davis, you said something about square roots over here, and I see a square root in this equation. Well, you do, but this is a coefficient. Coefficients can have square roots. Coefficients can have even fractions. All we care about in terms of the whole number part is the exponent. So all we're looking at are the exponents of x. And if you remember from Algebra 1, if I have a constant like 7, that's actually 7x to the 0 power. But since x to the 0 power is technically 1, it's the same thing as just 7. So constants are okay as well. And if you look at what is not a polynomial function, you'll see x is under a square root, you'll see x is in a denominator, you'll see negative exponents, and you'll see more x's in a denominator. Unfortunately, the only thing that they don't show us is that something like 2ix squared plus 3x minus I is also not a polynomial. Even though the exponents are whole numbers, we have non-real coefficients. So anytime anyone asks you, is this a polynomial? Two questions. Whole number exponents on x, real coefficients. If yes, polynomial. If not, no. So given that information, I'll give you a second to try to fill out questions 1 through 9. If you want to pause the video, go for it, and I'll pick up in a minute. Now that you've had a second, I am simply going to say, yes, it is a polynomial, or no, it is not a polynomial. Question 1, since I have an x under a square root, that would be a no. Number 2, I do have whole number exponents. I don't see an I, so yes, a polynomial. Number 3, the 15x squared is okay, but since there is an x under a square root here, the entire thing is not a polynomial. Question number 4, I have a whole number exponent here, but over here I have an x in an exponent. Well, this is not a polynomial. In fact, if it were just 3 to the x, we have a special term for that, which is an exponential function. And we'll return back to those in a couple minutes. Number 5, this would be no, because I have x's in a denominator. Number 6, hey look, a denominator must be a no. However, I don't see any x's down here. All we care about in polynomials are the x's. So, since none of the x's are in the denominator, yes, this is a polynomial. And of course, there are no i's. Number 7, x to the 5th, x to the 4th, x cubed, x squared, x. Yes, polynomial. X to the 5th is good, x to the 4th, x cubed, don't care about the 2/3, x squared, don't care about the square root, x, also good. And lastly, we have a bunch of x's underneath the square root, so we're going to have to say no. So at this point, if we were to swing back to our original warm-up, well, we would say yes, because it has whole number exponents and real coefficients. Now for our next two terms, I'm just going to rewrite our expression, 4x squared minus 2x minus 12. What is the degree? Well, the degree is defined as the highest number exponent on x. Highest exponent on x, which in this case is a 2. Therefore, the degree of this particular polynomial is 2. The leading coefficient is simply the coefficient or the number in front of the term that has the highest degree. So in this case, the leading coefficient is 4. Now, what we're going to do next is we are going to swing over to page 3, and we're going to take a look at how does the exponent and the coefficient impact something called end behavior, which means what happens as the graph heads off to positive infinity and what happens as we go to negative infinity. Now, first thing we're going to remind ourselves of are what linear, quadratic, and exponential functions look like. A linear function either goes from bottom left to top right or top left to bottom right and has an equation y is equal to mx to the first plus b. A quadratic is either an upwards or downwards facing parabola with y is equal to ax squared plus bx plus c. The important thing to note here is that a line has an odd exponent and a parabola has an even exponent. Or I should say an odd degree and an even degree. Finally, exponential functions are not polynomials. whereas linear and quadratic are polynomials. An exponential function has an x in the exponent. That's what tells us it's exponential. And these have a graph that asymptotes along the x-axis and exponentially grows, rockets straight up. Or you could have an exponential decay that comes from positive infinity and then asymptotes. So what we're going to do is we're going to look at 3 different cases. We're going to look at what happens in each of these cases when x is close to 0, when x is close to positive infinity, and when x is close to negative infinity. So in question 2, the first thing we're going to look at is what happens as these expressions go to 0. Now, if I were to plug in 0 for each x, well, 2 to the 0 is 1. 0 minus 20 is negative 20. 0 minus 0 plus 1 is 1. 0 plus 30 is 30. 0 minus 1 is negative 1. 0 plus 0 minus 4, negative 4. And 0 plus 0 is 0. Now, if I was to rank these from least to greatest, well, the least would be negative 20, then negative 4, negative 1, 0. Well, 1 and 1 tie for 5th, and I guess technically that's 7th place for positive 30. Now, here's the important thing. If x is 0, that coefficient, that number without x, has a massive impact. Basically, the bigger that number is, well, the bigger the whole expression is. Negative 20 was the smallest because that's the smallest constant. Well, second was negative 4. The next was negative 1. And you'll notice the trend actually continues. Whatever the constant was determined how big the overall function was. Huge impact. So let's see what happens as we go to positive infinity, a very large number. Now, a very large number is not 3 or 7 or 10. What we're talking about for a very large number is something like 100 or 100,000 or 100 million. We're talking about numbers that are astronomically huge. Now, unfortunately, our calculators can't handle numbers like this. The absolute highest I'm going to get is 30. Now, granted, that's really not very big. It's simply as big as my calculator can handle. So what I'm going to do is I'm going to go through all of these functions and I'm going to plug in 30 for x. And since I'm a cheat, I already plugged all of them in. So I'm simply going to write this list down. Now, if we take a look here, you'll notice that the smallest number didn't really match up. Well, the number that was the biggest up in number 1 is now the smallest down here. Well, and it's pretty darn close to the number that was the smallest. The whole order is messed up. Well, we've got 1,073,000,000 here with 2 to the x. The next closest is 24 million. That's a huge difference. Well, you look over here, it's got 809,000, and then we're all the way down to 20,000. These things are way too far apart. Well, what's the difference? Well, if we rank these from smallest to largest, the smallest being negative 810, then 60, 880, 27,000. And, you know, this is the largest. Here's what I want you to do. Write the degree of each. Write the degree of each. Again, degree is the highest exponent. Highest exponent. Take a second to do that. Well, here's the degrees. 2, 3, 4. Oh, I skipped this one. 809,000, so that should be 5. That'll be 6, and that'll be 7. So degree of 2, degree of 3, degree of 4, degree of 1, degree of 5, degree of 2. And this is exponential, so it doesn't have a degree. Hold on a second. 1 and 2, 3 and 4, 4 and 5, 5 and 6, exponential. Holy crap, they're the exact same lineup. The only thing that messes it up is over here, well, we have a negative in front of x squared. Other than that, whatever the degree was seemed to decide which one was biggest. That's pretty cool. Well, now we're going to try to plug in a negative number. We're going to go to negative infinity. So we're going to plug in x is equal to negative 30 and see what happens. Now, here's what I want to point out. I want you to notice something. Notice that x squared, x to the 4th, didn't change at all. And the negative x squared barely changed because of that 3x. Now, why would that be? Why is it that when I plugged in a negative number for x, these 3 didn't change? Take a look at the degree. All 3 of the degrees are even. So when all 3 of the degrees were even, it didn't matter if I was going to positive infinity or negative infinity, they stayed exactly the same. Well, when I did the same thing for the odd degrees, you'll notice that the odd degrees switched from a positive value to a negative value. Well, and over here, my exponential ended up flattening out to 0, just like the graph that we had looked at earlier. So, when comparing expressions, how does the order change depending on the values of x? So here's the crazy thing. When looking at an expression, heading to positive or negative infinity, the only thing that matters is the degree and sign of the leading coefficient. But exponential grows faster than a polynomial. Now let's see what this looks like in terms of, practically looking at a couple equations. Let's flip over to page 6. Keep in mind that we're going to look at something called end behavior. Now, we briefly looked at end behavior before, but basically, this is just a fancy way of saying mathy stuff. As x approaches positive infinity literally means as the graph goes to the right. As x approaches negative infinity literally means as the graph goes to the left. So we say as the graph goes to the right, f of x, or the y values, go to, well, you have two answers. If you say positive infinity, well, that means that the graph is going up. So it means that the graph is increasing in some way as you head to positive infinity, or as you head to the right. The other answer, well, could be negative infinity, which means that the graph is going down in some way. What's it there? That's what it is. Something like this. And then the third option is a number. And a number is when the graph asymptotes. So we really have three options. We can either say, as we go right, y approaches positive infinity, which means the arrow's going up, it's increasing. Negative infinity, which means the arrow's pointing down, or the graph is decreasing. Or we have a number, which requires an asymptote. So let's take a look at some of these functions here. Anytime you have something with an even degree, basically what happens is the graph kind of looks parabola-ish. So the graph is either going to be facing up or it's going to be facing down. And the thing that determines which direction it faces is the leading coefficient. So for example, if we have a positive leading coefficient, the graph will look like an upwards facing parabola. Now, is it possible that there's a little bump in the middle? Absolutely. Is it possible that the graph does some weird, crazy nonsense in between? Absolutely. But no matter what, if you have an even degree, the two ends of the graph, again, the end behavior, will have the graph pointing in the same direction, both being up. A negative leading coefficient simply means that the graph is going to be pointing down. And we can have the exact same crazy wobbliness in between, but really all we care about is the end behavior, or what's happening at the two farthest ends of the graph, completely ignoring what's happening in between. If we have an odd degree, well, keep in mind that x to the first is odd, which means even an odd degree looks like a line. So the simplest odd function is a line that's increasing. A cubic has that cool little curve shape that we've looked at in the past. And just like the even degrees, we can have some weird stuff going in the middle, except the ends will be pointing in the opposite direction. Again, that's why we call this end behavior. We only care about the two ends of the graph and not anything happening in between. And as you might expect, a negative leading coefficient still has the two ends of the graph pointing in opposite directions, except the two ends are decreasing instead of increasing, or we're starting from the top left and going down to the bottom right. Again, doesn't matter what happens in between. We're going to finish up by doing a couple quick example problems. Problems say, without a calculator, describe the end behavior of each function. So when it says describe end behavior, I know I'm going to be saying as x approaches positive infinity, f of x approaches something. As x approaches negative infinity, f of x approaches something. Now, in order to figure that out, all I really need to know are two pieces of information. What is the degree of the polynomial, and what is the sign of the leading coefficient? Now, since the degree is simply the largest exponent, I look at the exponents on my x's and pick the biggest number, 3. To find the sign of the leading coefficient, I look at that term of highest degree. If that first number is positive, I write positive. If that first number is negative, I write negative. Now, since the degree is a 3, which is odd, I know that the graph is either going to be going up and to the right or down and to the right. Basically, I know that the two ends are pointing in opposite directions. How do I know which one to pick? Well, it's the leading coefficient. If positive, the graph's going up. If negative, the graph's going down. So, since my leading coefficient is positive, I know that the end behavior of the graph looks like this. So, as x approaches positive infinity, as I go to the right, my graph is pointing up, or f of x approaches positive infinity. As x approaches negative infinity, which means as we look to the left side or the left end, that arrow's pointing down, so f of x approaches negative infinity. That's all we got to do. So let's look at question 2. Didn't mean to rhyme. The degree is the highest number exponent. I have a 6, a 3, and a 0, so the degree is going to be 6. Now, all I'm going to look at is the sign of the leading coefficient, which is the sign of that highest degree term, and it happens to be negative. Well, since the degree is even, I know it's going to be parabola-like in shape, or that both arrows are pointing in the same direction, either both up or both down. How can I tell the difference? Well, it's the leading coefficient. If positive, they're both pointing up. If negative, the ends are both pointing down. So since my leading coefficient is negative, my graph, or the ends of my graph, should look like this. So I would say as x approaches positive infinity, or as I go to the right, or the right end, f of x is pointing down, or towards negative infinity. As x approaches negative infinity, or the left end, if you'll notice, it is also pointing down, so f of x approaches negative infinity. That's all we have to do. So we look down at the next one. I see degree is going to be a 4, which makes the leading coefficient a positive number. Degree of 4 is both up or both down. And since the leading coefficient is positive, both ends are pointing up. As x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, which is that left end, f of x also approaches positive infinity. Last equation, last question, degree. Well, 7, 3, 2, 0. My degree is 7. So I look at that leading term. I have a sign of my leading coefficient that is negative. If the degree is odd, then my graph is odd-shaped, which means it's pointing in opposite directions. Positive is increasing, negative is decreasing. And since we're negative, our end behavior should look like this. So as x approaches positive infinity, or the right end, f of x is approaching, well, down, or negative infinity. Lastly, as x approaches negative infinity, f of x approaches, well, the left end is going up, so we say positive infinity. Hope that helps. Good luck on the homework, and if you need to stop, rewind, or rewatch the video, please feel free to do so.